Hello there, and welcome to the Science Owl Station channel. Today, we are about to undertake the quietest, most profound journey imaginable. We won't be moving an inch from where you rest, yet together we will voyage to the very edge of all that can be seen, to the outermost rim of light and time itself. Picture this, if you will. You are gently untethered from the pull of your bedroom, your town, your planet. You float backwards, slowly, watching the Earth shrink from a marble to a speck of blue dust until it is lost in the sun's glare. You drift further, past the silent orbits of Neptune and Pluto, beyond the cloud of icy comets that marks our solar system's doorstep. And as you turn to look back, you see not just our sun, but a sea of stars, a swirl of cosmic sand that is our home galaxy, the Milky Way. It's from this impossible vantage point that we begin to understand our true address in the cosmos and the nature of the frontier we seek, the edge of the observable universe. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel so inclined, I would love to know, where in the world are you listening from tonight? And what time is it for you? There's something deeply comforting in knowing we are all under this same vast ceiling, sharing this quiet exploration. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. The destination we speak of isn't a place you can point to on a map of the sky. It's not a wall or a fence or a great cosmic cliff. Instead, think of it as a horizon built not of land and sky, but of time and light. This is the ultimate horizon, the boundary of the observable universe. Everything we know, every star, every galaxy, every whisper of energy we have ever detected lies within this sphere. And its sheer scale is the first fact that should lull your mind into a state of wondrous awe. The observable universe has a diameter of roughly 93 billion light-years. Let that number settle. A light-year is the distance light, the fastest thing in existence, travels in 1 year about 9.5 trillion kilometers. Multiply that by 93 billion. The numbers become meaningless, abstract. They translate not into a distance we can comprehend, but into a feeling of profound, echoing spaciousness. How can it be 93 billion light-years across if the universe itself is only about 13.8 billion years old? This is our second fact, and it's the key to understanding this frontier. If light has had only 13.8 billion years to travel, we might expect to see only 13.8 billion light-years in any direction. But the space through which that light is traveling has itself been stretching, expanding, for all that time. Imagine a photon of light, a tiny messenger, setting off from a distant galaxy towards us. It's like a tiny ant starting to crawl across a vast, inflating rubber sheet. The ant moves at a fixed speed, but the sheet itself is stretching, making its journey much longer than it first appeared. By the time that ancient light finally reaches our telescopes, the galaxy that emitted it has been carried away by the expansion of space to a distance far greater than the simple travel time of the light would suggest. That 93 billion light-year figure is the current distance to the most distant objects whose light we can just now see. We are seeing them not as they are, but as they were in their infancy, and the space between us has ballooned tremendously in the intervening eons. This leads us to the third fact, the ultimate barrier that defines our cosmic horizon. We cannot see anything beyond a certain point because light from those regions simply hasn't had enough time to reach us since the universe began. The universe has a finite age, and light has a finite speed. This creates a fundamental limit to our perception. Beyond this horizon, the universe may very well exist. In fact, it almost certainly does, but it is disconnected from us in the causal flow of information. It is a realm of perpetual not yet from our perspective. The true edge, therefore, is not a spatial one, but a temporal one. It is the wall of time itself, and the oldest light in the universe is what paints that wall for us to study. And what is that oldest light? This is our fourth fact for tonight. The farthest, and thus the earliest, thing we can detect is not a galaxy or a star. It is a faint, cold, nearly uniform glow that permeates every cubic centimeter of the sky. We call it the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, cooled and stretched by the expanding universe over 13.8 billion years. It is the remnant of a time when the universe was a hot, dense, opaque soup of particles and energy. When it finally cooled enough for atoms to form and light to travel freely, that first burst of light set off in all directions. We are still bathed in it. When you see the static snow on an old television set tuned to a dead channel, about 1% of that chaotic signal is this ancient echo, the fossilized light from the dawn of time. It is the edge of our sight, the final luminous curtain beyond which we cannot directly peer. Every story we tell about the cosmos begins just after this curtain lifted. As you drift here in this imagined space between the galaxies, consider this fifth and final fact for this section. Every time you look up at the night sky, you are performing a remarkable feat of time travel. The pinprick of light from a star in Orion's belt left that star's surface about 1,200 years ago. The smudge of the Andromeda Galaxy is a portrait from 2.5 million years in the past. The faint, red-shifted galaxies at the limits of our largest telescopes are seen as they were over 13 billion years ago. The night sky is not a snapshot, but a mosaic of history, a layered archive of the universe's past. We are, in the most literal sense, cosmic archaeologists, sifting through layers of light to reconstruct a story that begins at the very horizon of our perception. And with that thought, let your breathing sink with this slow, timeless drift as we prepare to journey closer to that primordial glow, leaving that pervasive, ancient glow of the cosmic microwave background behind us as a distant memory, or rather, as the foundational backdrop to everything. We now turn our gaze forward into the expanse that gradually fills with structure. Our journey from the familiar to the frontier continues. We are now adrift in what feels like an ocean of darkness, but an ocean subtly textured by faint, distant currents. The Milky Way has long since faded into the tapestry of stars at our backs. Ahead, the first landmarks emerge not as sharp points, but as soft, ethereal smudges of light. We are entering the realm of the first islands in the cosmic sea, the galaxies. And our first waypoint, a ghostly island of stars slowly swimming into view, is our closest giant neighbor, the Andromeda Galaxy. This brings us to our first fact of this leg. The Andromeda Galaxy, known also as M31, is on a collision course with our Milky Way. But do not imagine a cataclysm of fire and shattered stars. Think instead of a slow, graceful, inevitable dance measured in cosmic time. It is approaching us at about 110 kilometers per second, drawn in by the mutual gravity of the two galaxies and the vast halo of dark matter that surrounds each. In roughly 4.5 billion years, they will begin to merge, their structures intertwining and eventually settling into a single, larger elliptical galaxy. For now, from our distant vantage, it appears as a serene, tilted spiral, a swirl of over 1 trillion stars, a mirror to our own home, and a reminder that even the grandest structures are not static, but are participants in a slow gravitational ballet. As we sail past Andromeda, the darkness ahead begins to sparkle with more of these faint, fuzzy patches. We are looking back in time, and as we look further, the galaxies appear smaller, bluer, more chaotic. This leads us to our second fact. The very first galaxies are thought to have begun forming when the universe was only about 400 million years old. These were not the majestic, well-ordered spirals we see today. They were likely small, fragile, and irregular mere nurseries of frenetic star formation, blazing with the light of massive, hot, short-lived first-generation stars. Their intense ultraviolet radiation worked tirelessly to ionize the neutral hydrogen fog that filled the universe, a process known as the epoch of reionization. We cannot see these infant galaxies directly with our eyes, even in this imagined journey, but our most powerful telescopes catch glimpses of them as tiny, red smudges, their light stretched and fatigued by its multi-billion-year journey. They are the pioneers, the first gatherings of matter after the Great Dark Age that followed the release of the CMB. To see in this deepening past, we sometimes rely on cosmic beacons. This introduces our third fact. Among the most luminous objects in the universe are quasars. The word is a contraction of quasi-stellar radio source, and for a long time, their true nature was a mystery. They appeared as star-like points of light, yet their spectra told a story of unimaginable distance and energy. We now understand them to be the fiercely active cores of extremely distant galaxies, powered by supermassive black holes. As vast amounts of gas and dust spiral inward at near-light speeds into these gravitational monsters, the material heats up to millions of degrees, creating an accretion disk that can outshine an entire galaxy of stars. A quasar is a lighthouse in the cosmic fog, its brilliant beam often directed by chance toward us, allowing us to see it across staggering distances. They are signposts from the universe's adolescence, marking a time when black holes feasted voraciously and galaxies were forming their central bulges. Their light, often emitted when the universe was less than 1 billion years old, carries clues about the conditions in those early, chaotic times. What guides the formation of these galaxies and draws them together? The answer brings us to our fourth and more subtle fact. The universe is woven together by an invisible scaffold of dark matter. We cannot see it, touch it, or directly detect it with any instrument we've yet devised, because it does not emit, absorb, or reflect light. Its presence is known only by its gravitational influence. It is the hidden architecture. We see galaxies spinning faster than they should if only their visible stars and gas were holding them together. We see giant clusters of galaxies whose gravity bends the light of objects behind them, an effect called gravitational lensing, with a strength that implies there is 5 times more mass than we can account for with luminous matter. This dark matter, we believe, formed clumps first after the Big Bang, creating gravitational wells into which ordinary hydrogen and helium gas could later flow, cool, and eventually ignite into stars, giving birth to the galaxies we see. It is the cosmic stage, unseen but essential, upon which the visible drama of stars and galaxies plays out. As you drift here, imagine feeling not emptiness, but the faint, pervasive gravitational tug of this vast, unseen web, a gentle pull structuring the void. And finally, a fifth fact to contemplate as the number of galaxy smudges around us seems to multiply. This early universe was a much more compact, intimate, and violent place. The galaxies we see at these great distances are not just far away in space. They are closer together in time. In the early epochs, the universe was denser. Galactic collisions and mergers were commonplace, driving the frantic star formation we see in those blue, irregular shapes. It was a time of construction, of building up the great structures from smaller pieces. The quiet, vast distances we associate with intergalactic space today were still being established, stretched into being by the relentless expansion of the universe itself. The frontier we are approaching was, in its own time, a bustling, energetic, and crowded construction site. The silence we project onto it is an illusion of distance and time. The light that now reaches us as a faint whisper was once a deafening roar of creation. Let that thought linger as we prepare to move beyond the realm of individual galaxies and into the grand architecture they collectively form, the large-scale structure of the cosmos itself. Our journey pulls us ever outward, leaving behind the familiar neighborhood of our local group, that small gathering of galaxies where the Milky Way resides. The sense of scale begins to shift in a profound and humbling way. Individual galaxies, those magnificent spirals and ellipticals, start to appear less as isolated islands and more like individual grains of sand on a vast, dark beach. And as we recede, a pattern emerges in their distribution. A pattern that reveals the true, colossal architecture of the cosmos. We are entering the realm of the universe's large-scale structure. The first fact that greets us here is one of staggering proportions. The universe is not a random scatter of galaxies. They are arranged in an immense cosmic web, with long, filamentary walls of galaxies intersecting at dense clusters, surrounding enormous, nearly empty regions called voids. And the largest single structure we have identified so far is known as the Hercules Corona Borealis Great Wall. Discovered by mapping gamma-ray bursts, the death throes of massive stars in distant galaxies, this Great Wall is a mind-numbing conglomeration of galaxies spanning approximately 10 billion light-years. To put that in perspective, it stretches across roughly a tenth of the entire observable universe. Its existence challenges some of our understanding of cosmology, as there is a theoretical upper limit to how large structures should be able to grow given the universe's age and the smooth initial conditions seen in the CMB. It is a reminder that the frontier is not just a place of light and distance, but of mysteries that test the very foundations of our theories. Floating here, we can contemplate the flip side of these great walls, the voids. This is our second fact. Cosmic voids are the true deserts of the universe, vast regions of space that can be 100 to 500 million light-years across and contain very few, if any, galaxies. They are not completely empty. They contain a sparse distribution of hydrogen gas and, undoubtedly, dark matter. But the density of matter here is far below the cosmic average. If you were born in a galaxy inside a void, your night sky would be profoundly, terrifyingly dark, with only a handful of neighboring galaxies visible. These voids make up the majority of the volume of the universe. The web-like structure we see is, in essence, the universe's matter having drained into the gravitational valleys, leaving behind these expansive empty bubbles. As you drift in this narrative, imagine the silence within a void, a silence deeper than any on Earth, a cosmological quiet where the gravitational pull from the surrounding walls is so faint, so diffuse, it feels like a static, directionless sigh. The universe is not a uniform soup. It is a sponge, and we live in the wet, dense parts. This brings us to a subtle but foundational third fact. The expansion of the universe is not happening from a central point into something else. This is a common misunderstanding. Instead, space itself is stretching uniformly at all points. A useful analogy is the surface of a balloon being inflated. Galaxies are like dots on that surface. As the balloon inflates, every dot moves away from every other dot. There is no center on the surface. Every point sees the same thing. This means the expansion rate, how fast two points are separating, depends on the distance between them. The farther apart two galaxies are, the more space there is between them to stretch, and so the faster they appear to recede from each other. This is why, from our vantage point, the most distant galaxies are fleeing from us at speeds that are a significant fraction of the speed of light. The expansion is everywhere, a gentle, relentless background process that sets the tempo for the cosmic dance. How do we know this expansion is real? The evidence is carried in the light itself, leading to our fourth fact, the cosmological redshift. As light travels through expanding space, its wavelengths are literally stretched along with the fabric of space-time. Think of a wave drawn on a rubber band. As you stretch the band, the wave's peaks and troughs get farther apart. Its wavelength increases. For light, an increase in wavelength means a shift toward the red end of the spectrum. The greater the distance the light has traveled, the more space has stretched during its journey, and the more redshifted it becomes. This redshift is not a Doppler effect from motion through space, like the changing pitch of a passing siren. It is an effect of space. It is the imprint of cosmic expansion on every photon that reaches us from the distant universe. When astronomers point their telescopes at a faint, fuzzy galaxy and analyze its light, they are essentially reading a barcode of stretched wavelengths that tells them not just how far away the galaxy is, but how much the universe has expanded since that light began its journey. It is the universe's most fundamental record-keeping system. And finally, a fifth fact to tie this all together. This large-scale structure we see, the walls, the filaments, the voids, is the amplified echo of the tiniest imperfections in the infant universe. Those subtle glimmers or density fluctuations we mentioned in the cosmic microwave background. They were the seeds, slightly denser regions imprinted in that primordial plasma had slightly stronger gravity. Over billions of years, they pulled in more and more matter, growing from tiny ripples into the vast clusters and walls we see today. The voids are the regions that were slightly less dense to begin with and got left behind as matter drained away. The entire majestic, sprawling architecture of the modern cosmos was written in code in the first hot glow after the Big Bang. We are seeing the result of a 13.8 billion year long chain reaction, a gravitational amplification of a whisper into a roar. As you let your mind wander across this web, imagine you can see not just the glittering nodes of galaxies, but the faint gravitational contours of the seed from which it all grew. A connection between the hottest, densest moment and the cool, structured vastness we navigate now. With that sense of deep connection, we can begin to sense our destination drawing nearer, that ultimate wall of light from which all these structures eventually emerged. The cosmic web begins to dissolve as we voyage further, its intricate filaments of galaxies growing sparse, the voids between them merging into a pervasive, uniform darkness. The glittering structures fade into the background, like city lights disappearing behind a thick, rolling fog. But this is not a fog of dust or gas. It is a fog of time. We are approaching the ultimate wall, not of brick or stone, but of liberated light. Our journey is about to reach its maximum depth, to the moment when the universe first became transparent. We are drawing near the cosmic microwave background, and the first fact to embrace here is that this glow is the oldest light we can ever see. It is not from the Big Bang itself, but from the moment roughly 380,000 years after it. Before this time, the universe was a searing, opaque plasma, so dense that photons, particles of light, could not travel any meaningful distance without colliding with a free electron. It was a brilliant, blinding fog. But as the universe expanded and cooled, electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the photons had a clear path. They decoupled from matter and streamed freely across the universe for the first time. That moment of emancipation is what we detect as the CMB. We are essentially seeing the afterglow of the universe's last scattering surface, a shell of light emitted from everywhere at once when it was a mere infant, a cosmic baby picture. As this primordial light washes over our imagined vessel, we encounter the second fact. It's profound, whispering cold. The CMB has a temperature of just 2.7 Kelvin, which is about minus 270.45 degrees Celsius. This is barely above absolute zero, the temperature where all molecular motion ceases. But it wasn't always this cold. When it was first released, the universe was at a temperature of about 3000 Kelvin, hot enough to glow a dull red. Over the ensuing 13.8 billion years, the expansion of space has stretched the wavelengths of that light enormously. Stretching a light wave makes it longer, and longer wavelengths correspond to lower energy and cooler temperatures. The vibrant, hot glow of the infant cosmos has been cooled and stretched into the frigid, microwave hum that permeates all of space. This means that even the deepest, darkest voids between galaxies are not truly cold and empty. They are filled with this faint, thermal radiation, a 3-degree bath of photons that is the ultimate baseline temperature of the universe. Every object in the cosmos, from stars to planets to drifting spacecraft, is immersed in it. But if this light is a uniform afterglow, how did anything ever form? How did we get from this smooth, hot soup to the clustered cosmos of galaxies and voids? The answer lies in the third crucial fact. The CMB is not perfectly smooth. It is exquisitely, almost impossibly uniform, but not perfectly so. When satellites like COBE, WMAP, and Planck mapped its temperature across the entire sky, they found tiny fluctuations, anisotropies, variations on the order of 1 part in 100,000. Imagine a pond of almost perfectly still water, with ripples so subtle they are barely perceptible. These minute temperature differences, slightly hotter spots and slightly cooler spots, correspond to regions of slightly higher and lower density in that early plasma. A slightly denser patch had a little more gravity, which pulled in a little more matter over the eons. These imperfections are the seeds of all cosmic structure. The hottest, densest spots in the CMB map are the precursors to the great superclusters and walls of galaxies we sailed past earlier. The cooler, emptier regions foreshadow the vast cosmic voids. The entire blueprint for the cosmic web was imprinted in that first light. This leads us to our fourth fact for this quiet approach. The patterns in the CMB are a frozen record of sound waves in the early universe. In that hot, dense plasma, matter and radiation were tightly coupled, creating a fluid that could support oscillations. Gravity would try to pull a dense region inward, while the intense radiation pressure would push it outward. This tug of war created standing waves, acoustic oscillations that rippled through the primordial soup. The CMB captures these waves at the moment they were frozen in place when the universe became transparent. The most common or fundamental wavelength of these sound waves was set by how far sound could travel in the plasma from the Big Bang until recombination, about 380,000 years. This distance appears on the CMB map as a characteristic scale of hot and cold spots. By measuring this scale, cosmologists can calculate the geometry and composition of the universe with incredible precision. It tells us the universe is flat. It tells us how much ordinary matter, dark matter, and dark energy there is. The CMB is not just a wall of light. It is the universe's first and most important fossil, and we are the paleontologists, deciphering its subtle ridges and valleys to understand the forces that shaped everything. As we now drift right up to this luminous curtain, let it fill your entire field of view. It is not a wall you can touch or pass through in any physical sense. To pass beyond it would be to travel back in time before light could travel freely into the opaque plasma of the universe's first 380,000 years. This is our fifth contemplative fact. The CMB represents a fundamental barrier to our observation, but not a barrier to existence. The universe extends beyond it in time, but not in directly observable light. It is the final page of a book written in photons. Every direction we look in the sky, our line of sight eventually terminates on this shimmering, redshifted surface. We are at the center of a sphere of this ancient light, not because we are special, but because we are observers in time. Any observer anywhere in the universe would sit at the center of their own observable sphere, bounded by their own shell of CMB. It is the most democratic of horizons. And as you contemplate being enveloped by this soft, cold glow from the dawn of time, feel its quiet uniformity, its gentle imperfections that held the promise of stars, planets, and, eventually, us. Let your breath slow, syncing with the profound stillness of this relic radiation, as we prepare to ponder what lies, shrouded and unseen, on its other side. We have reached the luminous curtain, the cosmic microwave background. But our journey through the story does not stop at this wall of light. Instead, we must now imagine what lies on its other side. We cannot see it, for light was not free to bring us pictures, but we can understand it. So let us gently, in our minds, cross this boundary, not by moving forward, but by turning back the clock. The cold, uniform glow around us warms, its microwaves shifting to infrared, then to visible light, then to a blistering, uniform glare. The universe is contracting around us in time, growing hotter and denser. We have passed beyond the last scattering surface, back into the era when the universe was an opaque, searing plasma. This is our first fact as we enter this hidden age. For the first 380,000 years of its existence, the universe was not transparent. It was a glowing fog, a dense soup of protons, electrons, and photons, constantly interacting. Light could not travel in a straight line. A photon would be born, travel a minuscule distance, and then be immediately scattered or absorbed by a free electron. It was a world of brilliant, diffused light with no clear images, no stars, no structure, just a uniform, hot brilliance in every direction. To be there would be to be suspended in an endless, blinding whiteout, a cosmic blizzard of energy. As the universe continues to shrink and heat in our backwards journey, we eventually reach a point, mere minutes after the Big Bang, where the conditions are so extreme that atomic nuclei begin to form. But let us pause our reverse chronology and instead flow forward again from that early moment, now inhabiting the unseen epoch that directly follows the release of the CMB. This brings us to our second fact. With the formation of neutral atoms, the universe did not simply fill with stars overnight. Instead, it plunged into a period known as the Cosmic Dark Ages. After the brilliant flash of recombination that created the CMB, the universe entered an era of profound darkness. There were no stars, no galaxies, no sources of light. The universe was filled with a mostly uniform sea of neutral hydrogen and helium gas, and the relic radiation from the CMB, which was rapidly cooling and redshifting. It was a quiet, expanding, and profoundly dark place. The only illumination was the fading, redshifted glow of the CMB itself, which would have shifted from visible red to infrared within a few million years, rendering the universe pitch black to human eyes. This was a time of waiting, of gravitational patience, as the tiny density fluctuations imprinted in the CMB began their slow work. What was the state of matter during these dark ages? This is our third fact. The universe was dominated by neutral hydrogen. This gas was not entirely uniform. It traced the same subtle density patterns seen in the CMB. In the slightly denser regions, dark matter, which had already clumped more decisively, provided a gravitational skeleton. Ordinary matter, in the form of this hydrogen gas, felt that pull. It began to very slowly drift, like mist settling into a valley, into these dark matter wells. The gas was cold, but as it became denser, a fascinating process occurred. Hydrogen atoms can absorb the very specific wavelength of light emitted when an electron flips its spin, a transition producing a line at 21 centimeters. This 21 centimeter radiation is a key tracer for this dark era. While we have not yet definitively mapped it from this early time, future telescopes hope to listen for this faint radio whisper from the dark ages, a direct signal from the neutral hydrogen fog that once filled all of space. It would be a map of the universe before the first dawn. The end of the dark ages was not a gentle sunrise, but a dramatic and transformative series of cosmic first lights. This leads to our fourth and pivotal fact. The first stars to ever form in the universe were not like our sun. Astronomers call them population 3 stars, and they were behemoths. Born from pristine clouds of only hydrogen and helium, with no heavier elements to help them cool and fragment efficiently, these clouds collapsed into stars of staggering mass, perhaps 100 to 1,000 times the mass of our sun. They were monsters burning hot and fast, with lives measured in mere millions of years. Their nuclear furnaces forged the first heavier elements in their cores: carbon, oxygen, nitrogen, and up to iron. And when they died, they did so spectacularly in supernova explosions of unimaginable power, seeding the surrounding gas with these newly forged atoms, the raw materials for future stars, planets, and life. The ultraviolet radiation from these first stars was intense and relentless. It is this light that brings us to our final fact for this hidden chapter. The intense UV light from the first stars and early quasars did something revolutionary. It began to rip electrons back off the neutral hydrogen atoms. This process, called reionization, began to clear the cosmic fog once more. This was the epoch of reionization, a drawn-out cosmic dawn that occurred between about 150 million and 1 billion years after the Big Bang. Bubble-like regions of ionized plasma, centered on the first stellar clusters and galaxies, began to grow and eventually overlap. The universe transitioned from being largely neutral to being almost fully ionized again, as it is today. However, this time the plasma was not dense and hot everywhere. It was a diffuse, warm medium punctuated by bright sources of light. The fog had lifted for good, allowing light to travel unimpeded across galactic distances. The dark ages were over. The universe had awakened, and its structure was now illuminated, ready to be seen by any future observer. The light from these very first luminous objects, stretched and faded by its epic journey, is what our most powerful telescopes like James Webb are now straining to detect. The first glimmers breaking through the darkness, the signposts of an ending that made our visible universe possible. Having witnessed, in our mind's eye, the first stars pierce the darkness and reionize the cosmos, we arrive at a profound juncture in our journey. We have followed the light to its very source, to the moment it was set free. But our exploration of the edge is not merely about what we can see. It is, perhaps more intriguingly, about what we cannot. We now stand at the limit of direct observation, facing the luminous wall of the CMB. But our minds and our science can venture further. We must now contemplate not just the observable, but the conceivable, the theories that stretch beyond the horizon of light into the realms of profound speculation rooted in mathematics and indirect evidence. Our first fact as we enter this conceptual frontier is a simple but staggering one. The entire universe is almost certainly much, much larger than the 93 billion light-year sphere we call the observable universe. In fact, it could be infinite. The part we see is just our cosmic neighborhood, limited by the finite speed of light and the finite age of the cosmos. But if we could instantaneously teleport to a galaxy at our current observable edge and look out from there, we would see another 93 billion light-year sphere of universe with its own CMB horizon, overlapping partly with ours but extending into regions forever hidden from our earthly vantage point. The true, full universe, if finite, must be at least hundreds of times larger than what we see, and if infinite, then it has no end at all. This is not fantasy. It is a direct implication of the cosmological principle, which states that, on large scales, the universe is homogeneous and isotropic. It looks roughly the same everywhere and in every direction. There is no reason to believe we occupy a special, central position in a small, finite cosmos. What process could have created such an immense, uniform reality from a singular beginning? This brings us to our second and pivotal theoretical fact: cosmic inflation. Most cosmologists believe that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Imagine the universe smaller than a proton, and then, in perhaps 10 to the power of -32 seconds, it inflates by a factor of at least 10 to the power of 26. This is not the steady expansion we see today. It was a burst of growth faster than the speed of light, which only limits motion through space, not the expansion of space itself. Inflation solves several major puzzles. It explains why the universe is so flat and why the CMB is so uniform. Regions now on opposite sides of the sky were once in causal contact before being inflated apart. But its most breathtaking implication is this: inflation didn't necessarily stop everywhere at once. The theory of eternal inflation suggests that while inflation ended in our pocket of the universe, giving rise to our Big Bang and everything in it, it may continue eternally in other regions, spawning an endless cascade of separate, disconnected bubble universes. Our entire observable cosmos might be just one bubble in a frothing, infinite multiverse. This leads naturally to our third contemplative fact: the multiverse. It is a concept that exists at the bleeding edge of cosmology and theoretical physics. It is not a single idea, but a suite of hypotheses. There is the chaotic inflation multiverse of eternal inflation, as just described. There is the many worlds interpretation of quantum mechanics, where every quantum possibility branches into a new reality. And there are ideas from string theory suggesting a vast landscape of possible universes, each with different physical constants and laws. The key point here is not to imagine parallel Earths or sci-fi portals, but to grasp the sheer, humbling scale of possibility. In an inflationary multiverse, some bubbles might have laws of physics utterly alien to ours, forces with different strengths, particles with different properties, dimensions that never stabilized. Some might be stillborn, collapsing instantly. Others might be vast, cold, and empty. Our universe, with its specific, life-permitting constants, could be a rare but inevitable oasis in an infinite desert of varied realities. We contemplate this not with excitement, but with a quiet curiosity, a recognition that the ultimate frontier may be a frontier of possibilities, not places. Could some of those other possibilities involve different numbers of spatial dimensions? This is our fourth fact to ponder. We are accustomed to 3 dimensions of space and 1 of time. But some theories, like string theory, require extra spatial dimensions for their equations to work, often proposing 10 or 11 dimensions in total. Where are they? The idea is they could be compactified or curled up on themselves at scales a billion times smaller than an atom. Alternatively, some dimensions might only be accessible to certain forces, like gravity. While this might seem like pure abstraction, it has a tangible connection to our edge. The very first moments of the universe, including the inflationary epoch, were when all dimensions, including any hidden ones, were potentially unfurled and interacting. The specific way our 3 spatial dimensions expanded to macroscopic size while others remained small may have been a random, quantum event during inflation, differing from bubble to bubble in a multiverse. The nature of our reality, including the number of dimensions we experience, might be a frozen accident from the first instance at the edge of time. We conclude this section with a 5th, synthesizing fact that brings us back to our starting point: the horizon. The reason we need theories like inflation is because of 2 glaring features of our observable edge: the horizon problem and the flatness problem. The horizon problem asks, why does the CMB look the same in all directions, even though regions on opposite sides of the sky were never in thermal contact according to standard Big Bang theory? Inflation solves this by stating they were in contact before a superluminal stretch drove them apart. The flatness problem asks, why is the universe so geometrically flat, a perfect balancing act between expansion and gravity? Inflation solves this by stretching any initial curvature to near zero, like blowing up a balloon to make its surface appear flat. Thus, our most successful theories about the very beginning are directly compelled by the properties we observe at the very edge of our sight. The frontier whispers clues about the origin. As you let these ideas of inflationary bubbles, hidden dimensions, and a potentially infinite whole swirl in the quiet of your mind, feel the scale not as something terrifying, but as something deeply peaceful. In an infinite multiverse, every possibility exists somewhere. But here, in this bubble, in this quiet moment, there is only the gentle hum of mystery and the soft light of ancient photons against the dark. We will now turn our gaze back from these speculative vistas, back into the realm of the seen, to trace how we have pieced together this story from our tiny vantage point. As we gently reel our perspective back from the vertiginous realms of eternal inflation and hidden dimensions, we find ourselves once more in the comforting domain of the observed, the measured, the meticulously mapped. Our conceptual vessel turns, and we are again floating in the expanse, but now we are equipped with a new understanding. The universe is not only a place of vast spaces, but also a grand, complex, and legible text. And its most important page, the one that sets the starting parameters for everything else, is the cosmic microwave background. Let us return to it now, not as a distant wall, but as an ever-present medium, a foundation. This is our first fact as we settle back into the observable. The CMB is not just a relic out there at the edge of sight. It is here, passes through this room, through you, through everything at this very moment. It is the ultimate background. If your eyes could see microwaves, you would not see a distant shell. You would see a uniform, faint glow coming from every direction, day and night. It is the universe's base temperature, a 3 Kelvin whisper against which all other cosmic signals are measured. Every observation of distant space is made by tuning our instruments to pick out specific melodies from this constant low hum. To read this text, we needed a translator of unparalleled sensitivity. This brings us to our second fact. One of humanity's greatest achievements in cosmic cartography was the European Space Agency's Planck satellite. Launched in 2009, Planck was not a telescope that looked at stars or galaxies in the conventional sense. It was a radio receiver, chilled to within a fraction of a degree above absolute zero, designed to listen to the faint microwave whisper of the CMB with more precision than ever before. For over 4 years, it scanned the entire sky, building a map of tiny temperature variations in the CMB, a map of the infant universe's density fluctuations. The final Planck map, released in 2018, is a mottled oval, like a cosmic dragon egg, displaying splotches of red, slightly warmer, and blue, slightly cooler. These splotches are not random. Their size and distribution are a Rosetta Stone. By analyzing the statistical properties of these patterns, the angular size of the most common hot and cold spots, cosmologists can extract fundamental truths about the universe. What are those truths? The third fact is a number that has become a cornerstone of modern cosmology: 13.8. That is the age of the universe in billions of years, as determined with remarkable precision from the Planck CMB data. This number isn't guessed. It is calculated from the details of the sound waves frozen into the CMB, combined with our knowledge of how fast the universe is expanding today. It tells us that the light from the CMB has been traveling for 13.8 billion years minus 380,000 years. It grounds our entire cosmic timeline. Every story about galaxy formation, stellar evolution, and the history of our own planet fits within this 13.8 billion year framework. It is the ultimate age of all things, the duration of the great story we are exploring. But the CMB tells us much more than just age. Its patterns reveal the universe's recipe, its inventory of contents. This is our fourth and perhaps most humbling fact. The universe, as we understand it from this primordial light, is composed of three primary ingredients. The first, and the one most familiar to us, is ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us. This is called baryonic matter, and it constitutes a mere 5% of the total energy density of the universe. Just 5%. The second ingredient is dark matter, the invisible gravitational scaffolding that holds galaxies and clusters together. It does not interact with light, but its gravitational pull is written into the way the CMB ripples evolved and the way galaxies later formed. It makes up about 27% of the universe. The dominant force, the majority shareholder in the cosmos, is the third ingredient, dark energy. This is the mysterious something causing the expansion of the universe to accelerate. It acts as a kind of anti-gravity on cosmic scales, and it accounts for roughly 68% of the universe. Let that settle. Everything we see, every galaxy, every nebula, every human, every atom, all of it is just 5% of the total. The other 95% is in forms we cannot see and do not fully understand. The CMB whispered this secret to us. It told us we are profoundly ignorant of the true nature of most of reality. How can we be so sure of these percentages from a map of baby universe wrinkles? The answer is our fifth fact for this section. The CMB is a snapshot of the universe at a single critical moment in its childhood. By measuring the exact sizes of the hot and cold spots, scientists can determine how the universe evolved from that moment to this one. The spots act like a cosmic ruler. Their apparent angular size on the sky depends on the geometry of the universe: flat, curved open, or curved closed, and the mix of matter and energy that has governed its expansion. The Planck data overwhelmingly points to a geometrically flat universe, and the only way to get a flat universe with the expansion history we see is to have precisely the mix of 68% dark energy, 27% dark matter, and 5% ordinary matter. Any other combination would bend the light differently, distorting the ruler, and the CMB patterns would not look the way they do. It is an elegant, powerful, and precise piece of forensic cosmology. We are like detectives who have found a fingerprint at the scene of the cosmic birth. From its unique swirls, we can deduce not just the identity, but the entire life story and inherent nature of the suspect, the universe itself. As we absorb this, feel the quiet confidence of that knowledge, a confidence born not from arrogance, but from patient listening to the oldest story there is, told in the language of temperature and light. From the cosmic backdrop, the uniform whisper of the CMB and the invisible dominance of dark energy and dark matter, we now turn our attention back to the visible, to that mere 5% of the universe that makes up the galaxies, stars, and light. But even within this slender slice of reality, at the very frontiers of our observable sphere, there exist inhabitants and phenomena that seem to defy the quiet order, cosmic wanderers and violent events that illuminate the nature of the edge itself. Our first travelers are the loneliest of stars, hypervelocity stars. These are suns, often massive and blue, hurtling through intergalactic space at speeds so great, over 1 million miles per hour, that they are unbound from the gravitational pull of their home galaxy. How does a star achieve such escape velocity? The leading theory points to a cosmic slingshot. a binary star system wandering too close to the supermassive black hole at the galaxy's center. The black hole's immense gravity can capture one star into a tight orbit, while violently ejecting its companion at a tremendous speed, like a stone from a sling. Imagine one of these stars, a brilliant blue-white beacon, sailing alone through the profound and empty darkness between galaxies. Its journey is one way, a permanent exile into the cosmic void. From our distant vantage, it appears as a solitary, speeding pinprick against the black, a reminder of the chaotic and violent interactions that can occur even in the hearts of galaxies, events powerful enough to cast entire suns adrift into the great intergalactic ocean. As we follow the path of such a star, we might encounter another class of cosmic wanderer, orphan galaxies. This is our second fact. Not all galaxies live in clusters or groups. Some, known as field galaxies or more poetically orphan galaxies, exist in relative isolation in the large-scale voids. They are islands in the emptiest parts of the cosmic sponge. How they formed there is a subject of study. Perhaps they were the sole winners in a small, local overdensity of dark matter, or perhaps they were gently ejected from a group long ago. These galaxies, often small and faint, experience a very different existence. With no nearby galactic neighbors, they are not subjected to the gravitational tides and mergers that shape galaxies in denser environments. Their evolution is slow, quiet, and isolated. If intelligent life arose in such a galaxy, its night sky would be almost devoid of other galaxies, a profound and perhaps terrifying solitude, with the Milky Way's view of Andromeda being an unimaginably rich tapestry in comparison. They are the hermits of the cosmos, dwelling in the deepest quiet of the voids. The forces that can create hypervelocity stars and disrupt galactic families often originate from the most enigmatic residents at the center of galaxies, supermassive black holes. This brings us to our third fact. Virtually every large galaxy, including our Milky Way, hosts at its heart a supermassive black hole, with masses ranging from millions to billions of times that of our Sun. These are not the vacuum cleaners of popular myth, but gravitational anchors. Their influence is dominant only in their immediate vicinity. At the edge of the observable universe, we see these monsters in their youth, powering the brilliant quasars we discussed earlier. But even in quieter, nearby galaxies, their presence is felt. They are the silent, dark engines around which galaxies pivot. Their formation is a key mystery. Did they grow from smaller black holes left by the first stars? Or did they form directly from collapsing clouds of primordial gas? Their existence is a fundamental part of galactic architecture, and their gravitational influence, though localized, can orchestrate stellar motions and, on occasion, launch stars into the abyss. Sometimes, however, the violence is not one of ejection, but of annihilation. At the very limits of our observable reach, among the most distant detectable objects, are the most powerful explosions since the Big Bang itself, gamma-ray bursts. This is our fourth fact. Lasting from mere milliseconds to several minutes, a gamma-ray burst, GRB, can outshine an entire galaxy of hundreds of billions of stars, releasing more energy in those few seconds than our Sun will in its entire 10 billion-year lifetime. We detect them as intense, fleeting flashes of the highest energy gamma-ray light. They come in two primary types: long-duration bursts, lasting more than 2 seconds, are thought to be the birth cries of black holes, signifying the catastrophic collapse of a massive, rapidly rotating star into a black hole producing powerful jets of radiation. Short-duration bursts are likely the result of two ultra-dense stellar remnants, neutron stars, colliding and merging. These events are so luminous they serve as cosmic lighthouses, visible across the universe. When we detect a GRB from a galaxy whose light has traveled for over 13 billion years, we are witnessing the death of one of the universe's very first stars, or a cataclysmic merger in the early cosmos. They are brief, violent signatures at the edge of time and space. What can these extreme wanderers and events tell us about the frontier? This leads to our fifth and synthesizing fact. Hypervelocity stars, orphan galaxies, quiescent supermassive black holes, and gamma-ray bursts all represent different aspects of the cosmic environment at its limits. They speak of gravitational dynamics, of isolation, of latent power, and of violent transformation. They remind us that the observable universe is not a static museum display, but a dynamic and often violent arena. The energy released in a gamma-ray burst, for instance, is so focused and immense that if one occurred within our own galaxy and its jet was pointed at Earth, it could potentially cause a mass extinction from thousands of light years away. Thankfully, they are rare and distant. These phenomena are the extreme expressions of the physical laws that govern the 5%. By studying them, especially at the greatest distances, we learn about the conditions in the early universe, the masses of the first stars, the merger rates of galaxies, the growth of black holes. The wanderers and the explosions are not just curiosities. They are probes. They illuminate the darkness at the edge, not with a steady glow, but with brilliant, fleeting flashes and the slow, steady trajectories of exiled suns, each telling a part of the story of how the cosmic frontier is shaped and what it contains. The tales of wandering stars and cataclysmic explosions bring us face to face with the fundamental currency of our cosmic journey: distance and its inseparable twin, time. To comprehend the edge, we must first grapple with the very units we use to map it. Let us begin with a deceptively simple term: the light year. This is our first fact, and it is crucial to dispel a common misconception. A light year is not a measure of time. It is a measure of distance. Specifically, it is the distance that a photon of light travels through the vacuum of space in 1 Julian year, which is approximately 9.46 trillion kilometers. When we say the Andromeda galaxy is 2.5 million light-years away, we are saying that the light we see tonight left Andromeda 2.5 million years ago and has been traveling across that immense gulf of space ever since. The term elegantly binds space and time, reminding us that to look out is to look back. Every measurement at the cosmic scale is, in essence, a form of archaeology. We are not seeing the universe as it is, but as it was at various points in its history, layered like the rings of a tree. This leads us directly to our second, more contemplative fact: the concept of look-back time. The farther away an object is, the longer its light has been traveling to reach us, and the further back in time we see it. This creates a cosmic timeline written in light. The sun? We see it as it was 8 minutes ago. The bright star Vega? 25 years ago. The Andromeda galaxy? 2.5 million years in the past, from a time when early humans were just beginning to walk the Earth. When the Hubble Space Telescope captures an image of a galaxy like GNZ 11, it is seeing it as it existed a staggering 13.4 billion years ago, when the universe was only about 400 million years old. We are not looking at a mature galaxy in its prime, but at an infant in the cosmic nursery. This means our map of the universe is also a history book. The edge of the observable universe is not just a spatial boundary. It is the beginning of the historical record, the first chapter we can possibly read. But how do we actually measure these unimaginable distances? We cannot stretch a tape measure across the void. This brings us to our third fact. The primary tool for measuring the vast distances to galaxies is cosmological redshift. As we've discussed, the expansion of space stretches the wavelength of light traveling through it. Astronomers use spectrographs to break the faint light from a galaxy into a rainbow-like spectrum. Embedded in that spectrum are specific dark or bright lines, the fingerprints of elements like hydrogen and calcium. By measuring how much these familiar lines have been shifted toward the red, longer wavelength end of the spectrum, they can calculate the redshift value, denoted as Z. A higher Z means greater stretching, which implies the light has traveled through more expanding space, and thus comes from a greater distance and a more ancient time. The most distant galaxies observed have redshifts greater than Z equals 10. This redshift is our odometer for the cosmos, a direct readout from the fabric of spacetime itself, telling us not just how far, but how long. However, there is a limit to this method, a horizon beyond which even this signal fades into nothingness. This introduces our fourth sobering fact, the cosmic event horizon. This is different from the particle horizon that defines the observable universe, the limit from which light has had time to reach us. The cosmic event horizon is a future boundary. Due to the accelerating expansion driven by dark energy, there will come a time for any given galaxy where it becomes so far away and receding so quickly that any new light it emits after a certain point will never reach us. The space between us is stretching faster than the light can cross it. We have already crossed this threshold for a great many galaxies. They are still visible to us now from light they emitted long ago, but any event happening in that galaxy today is forever beyond our future view. We are, in a sense, losing touch with parts of the cosmos in real time. The universe is not only showing us its past, it is gradually and permanently veiling its present from us, isolating cosmic regions from one another in a slow-motion divorce. We culminate this reflection on distance and time with a fifth, unifying fact. All these measures and horizons lead to one inescapable conclusion. We live inside a cosmic bubble of information. Our observable universe is a sphere defined by the finite speed of light and the finite age of the cosmos. Every observer anywhere in the universe sits at the center of their own such sphere. There is no privileged absolute center. This bubble is not static. It is dynamically defined by the expansion history. And as we look toward the edge of our bubble, we are engaging in an act of profound connection across time. The photon that finally lands on the sensor of the James Webb Space Telescope, having journeyed for over 13 billion years, completes a link between that primordial epoch and our curious present. In that moment, the distance collapses. The time between its emission and its detection is real, but the connection is immediate. As you breathe slowly in the dark, consider the photons from your bedside lamp traveling at that same universal speed limit. In a fraction of a nanosecond, they reach your eye. Now imagine that journey stretched across billions of years, from a time before Earth existed, from a star that may long since have died, its light steadfastly crossing an ever-widening gulf to tell you its story. That is the nature of our exploration. The distances are numbing, but the connection they facilitate is intimate. The edge is not a cold, remote wall. It is a whispering gallery of ancient voices, reaching us one photon at a time. As we contemplate the immense journey of photons, those steadfast messengers from the edge of time, we must also consider that their path is rarely a perfect straight line. The universe, for all its vast emptiness, is not optically empty. Space itself, the very stage upon which light travels, can be warped, curved, and bent by the presence of mass and energy. This brings us to our first phenomenon at this deeper layer of observation: gravitational lensing. Predicted by Einstein's theory of general relativity, it is the bending of light by gravity. Imagine space-time as a taut, flexible sheet. A massive object like a galaxy or a cluster of galaxies placed on that sheet creates a depression, a gravity well. When light from a more distant object passes near this well, its path is curved, much like a marble rolling past a depression would veer from a straight line. This means the light we receive from a distant galaxy can be distorted, magnified, and even multiplied. We might see multiple smeared or arc-like images of the same background object arrayed around the foreground mass. Gravitational lensing is not a flaw in our view. It is a powerful tool. It acts as a natural telescope, magnifying objects too faint and distant to see otherwise, and it serves as a scale, allowing us to weigh the invisible mass, primarily dark matter, of the lensing galaxy or cluster. The most elegant and striking manifestation of this is our second fact: the Einstein ring. When a distant light source, a foreground massive object like a galaxy, and our telescope align in a nearly perfect straight line, the bending of light can wrap the image of the background source into a complete or partial circle of light around the lens. It is a perfect halo of distorted reality. These rings are rare and beautiful cosmic mirages that confirm the profound connection between mass, space, and light. They are direct visual proof that mass curves the space through which light travels. Studying the exact shape and brightness of an Einstein ring allows astrophysicists to map the distribution of mass in the foreground lens with exquisite detail, revealing how dark matter is spread throughout the galaxy, often in a vast, smooth halo that extends far beyond the visible edge of the stars. The ring is a signature in the sky, a cosmic stamp that says, "Here lies hidden mass." This brings us squarely to our third and central character in this cosmic play: dark matter. We have spoken of its gravitational influence, but lensing allows us to trace its silhouette. Dark matter is the dominant form of matter in the universe, yet it remains shrouded in mystery. It does not emit, absorb, or reflect light of any kind. It interacts with ordinary matter and light only through gravity. We cannot see it, but we can see its effects on the rotation speeds of galaxies, on the motions of galaxies within clusters, and most distinctly on the bending of light. When we see a galaxy cluster acting as a powerful gravitational lens, distorting the images of hundreds of background galaxies into long, faint arcs, the amount of bending tells us the cluster's total mass. When we then add up the mass of all the visible stars and hot gas in the cluster, we find it accounts for only about 1/5 of the total needed to produce that bending. The rest is dark matter. It is the unseen skeleton, the hidden framework that holds the largest structures together and sculpts the paths of light across the cosmos. Its nature, whether it is a sea of exotic particles, a modification of gravity, or something else entirely, is one of the greatest puzzles at the frontier of physics. If dark matter's gravity pulls things together, shaping the cosmic web, there is a countervailing force at work on the very largest scales. This is our fourth fact, the most dominant component of the cosmos: dark energy. We've mentioned it as the driver of accelerated expansion, but its nature is even more elusive than dark matter's. Dark energy is not a clumping, pulling force. It appears to be a property of space itself, a constant energy density, a kind of anti-gravity that causes empty space to repel itself. As the universe expands and more space comes into existence, the total amount of this repulsive energy increases, leading to an ever faster expansion. Its effects are negligible within galaxies or even clusters, where gravity reigns supreme. But in the vast, near-empty tracks between galactic superclusters, dark energy's gentle, relentless push dominates. It is the reason the cosmic event horizon exists, the reason distant galaxies will one day fade from view. It is the reason the universe's long-term fate appears to be one of increasing isolation and cold. Dark energy determines the ultimate geometry and destiny of the cosmos, yet we know almost nothing about what it is. It is the quiet, dominant background hum of reality, shaping the grandest stage of all. Weaving these threads together, lensing dark matter, dark energy, gives us our fifth and synthesizing fact. Our view of the edge is a complex tapestry woven by these invisible forces. The light from the most distant galaxies does not simply fly to us unimpeded. It may be magnified by the gravitational lens of an intervening cluster of galaxies and dark matter, bringing into view objects that would otherwise be forever beyond our grasp. That same cluster's mass, dominated by dark matter, is itself being pulled upon by the gravity of other large-scale structures, while the space between all these structures is being stretched by dark energy. When we finally detect that ancient, lensed photon, its journey tells a story not just of its source, but of every gravitational valley and hill it traversed, and of the expanding landscape it crossed. The frontier is not a clean, sharp line. It is a shimmering, distorted, and magnified view, filtered through the invisible architecture of dark matter and set against the accelerating backdrop of dark energy. To observe the edge is to engage in a form of cosmic tomography, using light to probe the unseen layers of the universe. As you rest here, imagine your perception gently bending, not with stress, but with the serene curvature of space-time itself, feeling the invisible tug of hidden masses and the soft, expansive push of the vacuum, all guiding the ancient light to your mind's eye. The journey through the grand, invisible architecture of the cosmos, through lensing halos, dark matter webs, and the push of dark energy, can feel abstract, a ballet of forces on a scale that defies human intuition. It is time now, in our narrative, to turn this vast perspective inward, to begin the long, slow journey home. Not to a house or a city, but to a galactic neighborhood, to a single star, to a tiny, rocky planet. Let us pivot our gaze away from the distorting lenses and the receding horizon. Let us sail back along the river of light, from the primordial and the immense, towards the local and the familiar. Our first landmark on this return is not a single point, but a vast, swirling collection of them, the Milky Way galaxy. And our first fact upon re-entering its domain is one of scale within scale. From our earlier vantage, we learned the observable universe contains perhaps 2 trillion galaxies. The Milky Way is just one of them, but within that one galaxy, there are an estimated 100 to 400 billion stars. Let that sink in. For every grain of sand on all the beaches of Earth, there are more stars in our home galaxy. And our sun, the anchor of our lives, is just one of those hundreds of billions. We are returning from a cosmos of trillions of islands to a single island, itself an empire of stellar fires. As we draw closer, the structure of our galaxy resolves from a faint, distant smudge into a majestic spiral. We see it now from above its disk, a vast pinwheel of starlight, with spiral arms traced by blue clusters of young, hot stars and glowing pink nebulae where new stars are being born. At its brilliant, crowded core lies a central bulge of older, yellower stars. And surrounding it all is a vast, diffuse spherical halo of ancient stars and globular clusters, permeated by the dominant presence of dark matter. Our second fact is about location. Our solar system does not reside in a special place. We are about halfway out from the center to the visible edge, nestled in a minor spiral arm called the Orion Cygnus Arm, or simply the Orion Spur. We orbit the galactic center roughly every 230 million years, a period known as a cosmic year. The last time our planet was in this same position in the galaxy, the dinosaurs were just beginning their rise. Our position is ordinary, which, in the cosmic sense, is profoundly comforting. We are not at the center. We are participants in a slow, grand rotation, part of the great, gravitationally bound dance of our spiral city. This sense of motion brings us to our third, more immediate fact. Even as we speak, you are not still. You are moving at tremendous speeds, yet you feel nothing. The Earth rotates on its axis, giving us day and night, but it also revolves around the Sun at about 107,000 kilometers per hour. Feel that for a moment. You are on a planet hurtling around a star at a speed that would circumnavigate the Earth at the equator in less than 25 minutes. This orbital motion is our most intimate experience of cosmic velocity. It is a clean, elliptical path governed by the Sun's gravity, a yearly rhythm so reliable we base our calendars upon it. Yet, this is just one layer of our journey. For the Sun itself is not stationary at the center of our celestial orbit. This is our fourth fact. Our entire solar system is in motion within the Milky Way. We are orbiting the galactic center at about 720,000 kilometers per hour. But even this orbit is not a simple circle in a flat plane. The galaxy's disk undulates, and our Sun, along with its planetary entourage, bobs up and down through the plane of the disk as it goes around, completing a vertical oscillation every 60 to 70 million years. Some scientists have speculated that these periodic journeys through the denser midplane of the galaxy, where interstellar gas and dust are more concentrated, could influence Earth's climate through increased cosmic radiation or comet disturbances, potentially correlating with mass extinction events. Our motion is a complex, weaving path, a ride on a carousel that itself is on a Ferris wheel with a gentle, slow-motion bounce. We culminate this return to the local with a fifth fact that ties our galactic journey to our daily experience: the quiet constancy of the night sky. The stars that form our constellations are our relatively close neighbors within the Milky Way's disk. They are so distant that their positions relative to each other appear fixed in a human lifetime, creating the familiar patterns we've named. But over tens of thousands of years, their proper motions, their actual movements through space, will distort and eventually erase the constellations we know. The Big Dipper will slowly unbend. Orion's belt will tilt, The sky is a slowly turning kaleidoscope on a timescale that dwarfs civilizations. Yet, for us, it is a tableau of permanence, a ceiling of familiar lights. This is the gift of our return from the edge, a sense of place, of neighborhood, of a stable celestial stage against which the drama of our lives plays out. The mind-bending vastness and violence of the cosmic frontier are filtered into a serene, starry peace. As you picture our solar system's multi-layered voyage, spinning, orbiting, bobbing, circling, feel not dizziness, but a deep, rhythmic calm. You are on a planet in motion, around a star in motion, within a galaxy in motion, all moving with a grace and predictability that has persisted for billions of years. It is a gentle, cosmic lullaby of orbital mechanics. From the familiar constellations and the steady, multi-layered motion of our solar system, we now gently expand our view once more. But this time, not back toward the unknowable edge, but rather to our immediate cosmic community. We have returned to our star, to our galaxy. Now let us meet our neighbors. Our first fact is one of local geography. The Milky Way is not alone in this region of space. We are part of a small, gravitationally bound family known as the local group. This group spans about 10 million light-years in diameter and contains roughly 54 galaxies, though most are tiny dwarf galaxies. The two giants are our Milky Way and the Andromeda Galaxy, M31. The third largest is the Triangulum Galaxy, M33, a beautiful spiral. The rest are satellites orbiting these giants or floating in the gravitational hinterlands between them. Think of it as a quiet archipelago in the vast cosmic ocean. Our galaxy and Andromeda dominate with their entourages of smaller galaxies. The Large and Small Magellanic Clouds are our most famous satellite galaxies, visible as fuzzy patches in the southern hemisphere's night sky. This group is our home cluster, a gathering where gravity has overcome the general expansion of the universe, binding us together in a slow, mutual dance that will eventually lead to mergers and a single, larger galaxy. If the local group is our archipelago, then it sits within a much larger continent. This brings us to our second fact. Our local group is but a tiny part of the Virgo supercluster. A supercluster is a vast collection of galaxy groups and clusters, bound together by gravity on the largest scales. The Virgo supercluster is named for the Virgo cluster, a dense knot of over 1,000 galaxies at its heart, about 54 million light-years away. Our local group lies on the outskirts of this immense structure, which spans about 110 million light-years. For decades, this was considered our cosmic address. Planet Earth, Solar System, Orion Spur, Milky Way Galaxy, Local Group, Virgo Supercluster. It gives a sense of place, of belonging to an immense but finite structure. Within this supercluster, all galaxies are streaming very slowly inward, toward the densest regions, pulled by the collective gravity of the mass concentrated there, particularly in the Virgo cluster itself. But recent, more precise mapping has revealed an even larger context, and this is our third fact. The Virgo supercluster itself is just a lobe, an appendage of a far vaster structure called the Laniakea supercluster. In Hawaiian, Laniakea means immense heaven. Discovered in 2014 by analyzing the peculiar motions of galaxies, Laniakea is a galactic supercontinent spanning about 520 million light-years and containing roughly 100,000 galaxies. Its gravitational heart is not the Virgo cluster, but a region known as the Great Attractor, which lies about 150 to 250 million light-years away, obscured by the dense plane of our own Milky Way. The Great Attractor is not a single object, but a concentration of mass equivalent to tens of thousands of Milky Ways, a gravitational focal point toward which our entire supercluster, along with others, is slowly flowing. We are part of this immense, slow river of galaxies, drifting toward a point we cannot clearly see, pulled by the sheer weight of matter in that direction. Our motion is not random. It is a gentle cosmic pilgrimage toward a hidden, massive center. What defines the borders of a supercluster like Laniakea? The answer lies in the motions of galaxies themselves, and this leads to our fourth fact about large-scale structure. The universe is organized into a cosmic web of filaments and voids, often described as having a honeycomb or sponge-like structure. Superclusters like Laniakea are not isolated islands. They are the densest nodes in this web, where multiple filaments intersect. These filaments are long, thin strands of galaxies and dark matter, connecting superclusters across billions of light-years. Between them are the voids, the vast, nearly empty bubbles we discussed earlier. Our position within Laniakea places us on a filament, streaming along it toward the nodal concentration of the Great Attractor. This web is the largest pattern in nature, the visible expression of the dark matter skeleton upon which ordinary matter has condensed. When you look at a modern map of the universe showing millions of galaxies, you are not seeing a random scatter. You are seeing the delicate filamentary threads of this web, with glowing beads of galaxy clusters strung along them. We conclude this survey of our cosmic address with a fifth synthesizing fact that brings scale back to a human feeling. In this immense hierarchy, from planet to star to galaxy to group to supercluster to web, we occupy a profoundly typical place. There is nothing special about our location. We are not at the center of the local group, nor the Virgo supercluster, nor Laniakea. We are in the suburbs. This cosmological principle that we do not occupy a privileged position is a cornerstone of modern astronomy. It is a humbling and equalizing idea. Every point in the universe has its own observable horizon. Every galaxy is part of some group or cluster. Every cluster is part of some filament flowing towards some larger attractor. Our immense heaven, Laniakea, is just one of many such superclusters in the observable universe. This typicality is, in a way, comforting. It means the physical laws we deduce here are the same everywhere. It means the universe is knowable. And it means that the quiet, starlit night you see from your window is a view shared in principle from countless other planets in countless other suburban galactic neighborhoods, each with its own constellations, its own stories, and its own gentle gravitational drift through the dark, silent currents of the cosmic web. Having charted our place within the grand, flowing continent of Laniakea, we now turn from the cosmos itself to the means by which we have come to know it. How does a species on a tiny rock, orbiting an ordinary star, come to understand the edge of the observable universe? Our knowledge is not gifted. It is painstakingly gathered, photon by photon, whisper by whisper, by a suite of extraordinary instruments, both in space and on the ground, that act as extensions of our senses. Our first tool is perhaps the most iconic, the Hubble Space Telescope. Launched in 1990 and initially hobbled by a flaw in its main mirror, Hubble's repair and subsequent decades of operation revolutionized our view of the cosmos. Its greatest gift was its location, above Earth's blurring atmosphere. This allowed it to take exquisitely sharp, deep images of the distant universe. Its most famous contribution to our quest for the edge is the Hubble Ultra Deep Field. In 2004, Hubble pointed at a seemingly empty patch of sky near the constellation Fornax, a region no bigger than a grain of sand held at arm's length. For a total exposure time of over 11 days, it gathered the faintest light. The resulting image was not black. It was filled with over 10,000 galaxies of all shapes, sizes, and colors, a cosmic core sample stretching back to within 1 billion years of the Big Bang. That single image drove home the sheer abundance of galaxies and gave us our first deep statistical census of the early universe. Hubble taught us to see the frontier not as an abstract line, but as a populated, evolving place. But Hubble had its limits. The most distant galaxies are not just far away. Their light is stretched so severely that it falls into the infrared part of the spectrum. To see further back, we need an eye tuned to that infrared light. This brings us to our second fact and our newest, most powerful time machine. The James Webb Space Telescope, JWST, launched on Christmas Day 2021. JWST is Hubble's spiritual successor, but designed with a singular focus on the infrared. Its golden, segmented mirror is over 6 times larger than Hubble's light-collecting area, and it orbits at a special point called L2, far from Earth's interfering heat. JWST's mission is to peer into the cosmic dawn, the epoch of the first stars and galaxies. It is already doing so. Where Hubble saw fuzzy red smudges at the limits of its vision, JWST resolves them into distinct, often strangely shaped infant galaxies. It is analyzing the chemistry of atmospheres on exoplanets and peering through dust clouds to watch stars being born. Most importantly for our journey, it is looking for the sources that reionized the universe, the first generation of stars that burned away the primordial fog. JWST is our current vanguard at the edge, pushing the boundary of the observable back to within a few 100 million years of the beginning. While space telescopes capture the faint light of the early cosmos, other instruments on Earth listen to a different kind of signal. This is our third fact. The universe speaks in more than just visible and infrared light. Radio telescopes, with their vast parabolic dishes, tune into the long wavelength radio waves emitted by cold gas, pulsars, and the faint echo of the universe's infancy. Projects like the Atacama Large Millimeter/Submillimeter Array ALMA in Chile use dozens of synchronized radio dishes to achieve incredible resolution, allowing us to see the details of planet-forming disks around young stars and the cold, dusty hearts of distant galaxies. But for the very edge, radio astronomers dream of detecting the 21-centimeter line from the neutral hydrogen of the cosmic dark ages, a signal that has been traveling for over 13 billion years and is now stretched to meter-long wavelengths. Detecting this signal is one of the holy grails of cosmology, as it would provide a direct, three-dimensional map of the universe before the first stars lit up. It is a whisper from the dawn, and we are building ever more sensitive antennas to try to hear it. Some cosmic events, however, don't primarily announce themselves with light at all. They shake the very fabric of space-time. This brings us to our fourth, groundbreaking fact: the detection of gravitational waves by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. Predicted by Einstein, gravitational waves are ripples in space-time caused by the acceleration of massive objects, like two black holes or neutron stars spiraling into each other. When such a merger occurs, it sends out a chirp, a literal stretching and squeezing of space itself that travels at the speed of light. LIGO uses lasers traveling down long, perpendicular vacuum tubes to detect these minuscule distortions, smaller than a proton. The first direct detection in 2015 opened a new window on the universe. We are no longer just astronomers, we are cosmic listeners. This new sense allows us to hear events that are electromagnetically dark, like the merger of two black holes. It provides a direct test of gravity in its most extreme regime and a new way to measure cosmic distances. While most detected events are from within our cosmic neighborhood, future space-based gravitational wave observatories could detect the ripples from the mergers of the very first supermassive black holes, offering a completely different perspective on the early universe. From Hubble's deep fields to JWST's infrared gaze, from ALMA's cold scrutiny to LIGO's sensitive listening, our fifth and synthesizing fact is this: understanding the edge of the observable universe is a feat of multidisciplinary triangulation. No single instrument tells the whole story. We combine the optical history from Hubble, the infant galaxy spectra from JWST, the gas maps from radio telescopes, and the space-time ripples from LIGO to build a coherent, multisensory picture of the cosmos from its birth to the present. Each tool corrects and refines the others. Each new window reveals surprises that force us to rethink our models. This vast, collaborative endeavor, involving thousands of scientists and engineers across the globe and in orbit, is how a conscious part of the universe attempts to understand its own origins and extent. It is a slow, meticulous, and profoundly human enterprise. As you rest, imagine these silent sentinels: the gleaming telescope in the void, the stark white dishes on a high desert plain, the laser-lit tunnels waiting for a tremor in space-time, all pointed outward, listening, watching, gathering stories from the edge, so that we, here in the quiet dark, might know them. From the silent, listening observatories and the brilliant eyes of our space telescopes, we have gathered mountains of data, painting a picture of the cosmos that is both stunningly detailed and profoundly puzzling. We have mapped the edge, traced the large-scale structure, and peered back to the first glimmers of light. Yet, the more we see, the more we realize how much we do not see. The frontier of our knowledge is not just a place in space, but a boundary in understanding. We are now left facing the great, unanswered questions that linger at the edge of the observable, the mysteries that our instruments have revealed but not yet solved. Let's begin with the most tangible ghost in the cosmic machine: dark matter. We have felt its gravitational hand in the rotation of galaxies, in the binding of clusters, in the bending of light. But our first and most persistent question remains: what is it? We know what it is not. It is not made of atoms. It does not interact with light or with ordinary matter in any way except through gravity. It is cold, meaning it moves slowly, allowing it to clump and form the cosmic scaffolding. The leading candidate is a hypothetical particle called a WIMP, a weakly interacting massive particle. Billions of these particles might be streaming through your body every second, yet they pass through without a trace. Deep underground, in labs shielded from cosmic rays, experiments wait in profound silence, hoping to catch the unimaginably rare collision of a WIMP with an atomic nucleus. So far, they have heard nothing. Dark matter remains a silhouette, a shape defined only by the absence of light, the most dominant form of matter in the universe, and a complete mystery. If the nature of matter is mysterious, the nature of space itself is even more so. This brings us to our second great question. What is dark energy? It is not a clumping force like gravity, but a property of empty space, a constant energy density causing the expansion of the universe to accelerate. Is it the cosmological constant that Einstein once proposed and then discarded, a fundamental property of the vacuum? Or is it a dynamic field nicknamed quintessence that could change over time? The difference is cosmic. A true cosmological constant means the acceleration is fixed, and the universe will expand forever into a cold, dilute future. A dynamic field could decay or strengthen, leading to different fates, perhaps even a future Big Rip. Our best measurements from the CMB and distant supernovae are consistent with a cosmological constant. But the uncertainty is still large enough to allow for other possibilities. Dark energy is the dominant component of the universe, shaping its ultimate fate, and we have no idea what it is. It is the quiet, repulsive breath of nothingness, and it is winning the cosmic tug of war. These questions about content lead to a question about container. Our third great mystery is the shape of the universe. Is it flat, like a sheet of paper? Is it positively curved, like the surface of a sphere closing in on itself? Or is it negatively curved, like a saddle expanding forever in a hyperbolic shape? All our observations, most precisely from the CMB, indicate a universe that is geometrically flat to within a razor-thin margin. A flat universe is infinite and will expand forever. But here's the puzzle. For the universe to be so perfectly flat today, it must have been unimaginably, impossibly flatter in its first moments. This flatness problem was one of the key motivations for the theory of cosmic inflation, which stretched any initial curvature smooth. So we think it's flat, but is that a local condition? Could the greater, unobservable universe be curved? And if it is flat, does that truly mean it is infinite? Our minds recoil from infinity, yet the data points that way. The shape of all that exists remains a profound philosophical and mathematical frontier. The possibility of a universe beyond our own forms our fourth contemplative question. Does the multiverse exist? We discussed it as a consequence of eternal inflation, the idea that our Big Bang was just one bubble in a frothing, endless meta-universe. But is this science or philosophy? Scientists argue that if a theory like inflation naturally and inevitably predicts multiple universes with different properties, and if that theory is our best explanation for observable features of our universe, like its flatness and uniformity, then we must take the prediction seriously. However, by definition, other universes are causally disconnected from ours. We can never observe them directly. This puts the multiverse in a strange place. It may be a logical implication of our best physics, yet it may be forever untestable. It stretches the definition of science itself. The multiverse question forces us to confront the limits of knowledge. Are there truths about reality that are fundamentally, permanently beyond our empirical grasp? We culminate this list of mysteries with a fifth, more subtle but deeply personal question that arises from all the others. Why this universe? This is the question of fine-tuning. The constants of nature, the strength of gravity, the mass of the electron, the energy in the vacuum, seem exquisitely balanced to allow for the existence of stars, planets, and life. If they were slightly different, atoms wouldn't form, stars wouldn't ignite, and complexity would be impossible. Why? One answer is the anthropic principle. We observe a universe compatible with our existence because we are here to observe it. In a multiverse with countless universes of varying laws, a few, by sheer chance, will have the right numbers for life. We live in one of them. Another answer is that a deeper, unified theory will show these constants are not arbitrary but inevitable. Or perhaps there is a purpose, a reason beyond physics. Science cannot answer the why in a teleological sense. It can only describe the how. But the eerie precision of the cosmic recipe lingers as a silent, profound question at the heart of everything we see. As you ponder these mysteries, the unseen matter, the repulsive vacuum, the shape of everything, the possibility of other everythings, and the reason for this particular something, let them not trouble you. See them instead as the soft, open edges of the known, the spaces where wonder comfortably resides. The universe is under no obligation to make sense to us, yet it has given us minds curious enough to ask, and to find a strange peace in the not knowing. We will now slowly turn from these looming questions back toward the narrative of our own story within this mysterious cosmos. Having dwelled among the great unanswered questions, the what of dark matter, the why of dark energy, the shape of the all, and the possibility of a multiverse, we find our perspective subtly shifting. We have looked back to the beginning and scrutinized the present. Now, with the same gentle curiosity, let us cast our gaze along the arc of time, not backwards but forwards. Let us contemplate the future of the universe, not with dread, but with the serene acceptance one might feel watching the slow, inevitable changing of seasons. The cosmic story does not end with us, here, now. It stretches into a future so vast it makes the 13.8 billion years of the past seem like a brief prologue. Our first fact on this forward journey is both simple and profound. The expansion of the universe will continue. Driven by dark energy, the space between galaxy clusters will stretch ever wider. This is not a guess. It is the clear trajectory written in the redshift of distant supernovae and echoed in the CMB. The galaxies we see today, already racing away, will recede faster and faster. The cosmic web, that beautiful filamentary structure, will not collapse. It will be pulled apart. The bonds of gravity that hold together our local group will remain, but the connections to other superclusters will stretch, thin, and eventually snap from view. The universe is not contracting. It is unfurling. As this unfurling proceeds over billions of years, a profound change will come to any hypothetical observer. This is our second fact. The night sky will grow darker, not in a human lifetime, nor in a million, but over many billions of years. As galaxies are carried beyond our cosmic event horizon, their light will no longer be able to reach us. They will not vanish in a flash. They will slowly redshift into invisibility. Their light stretch to longer and longer wavelengths until it carries too little energy to detect, fading like a forgotten note. First, the distant clusters will disappear. Then, over eons, even the galaxies of the Virgo supercluster, beyond our local group, will slip beyond the horizon. In a future so distant it is hard to conceive, the only galaxies left in the sky of the Milky Way, or its merger remnant with Andromeda, will be its own satellite galaxies, bound by gravity. The grand tapestry of the cosmic web, the evidence of the vast universe we now know, will be hidden. The sky will become a lonelier, though still beautiful, place. What of the stars within the galaxies that remain bound together? This leads to our third fact. Star formation is a finite chapter in the life of the universe. Stars are born from clouds of gas and dust. As galaxies age, they use up this raw material. Great spiral galaxies like ours will eventually, over hundreds of billions of years, exhaust their interstellar gas. The brilliant blue nurseries of new stars will wink out one by one. The galaxies will gradually redden as only the longer-lived, cooler stars remain. The smallest stars, red dwarfs, are incredibly frugal with their nuclear fuel, shining for trillions of years. They will be the last generation, the enduring embers of the stellar era. But even they are not eternal. Slowly, over timescales that dwarf the current age of the universe, the last red dwarfs will also burn out, becoming faint white dwarfs that cool over eons into black dwarfs, cold, dark spheres of crystallized carbon and oxygen. The era of stars, the epoch that defined our cosmos and made our existence possible, will come to a quiet close. We arrive then at the fourth and perhaps most poetic fact. The long-term fate of the universe, based on our current understanding, is often termed the heat death. This is a misnomer. It is not a fiery end, but a cold one. It is the ultimate state of maximum entropy. Imagine a cup of hot coffee left in a room. It eventually cools to room temperature, not because the heat disappears, but because it spreads uniformly throughout the room. The universe is doing the same on a cosmic scale. All energy gradients, the difference between hot stars and cold space, between ordered structures and chaotic void, will eventually even out. All nuclear fuel in stars will be spent. Black holes, the last reservoirs of concentrated mass and energy, will themselves evaporate over incomprehensible timescales via Hawking radiation, slowly dissipating into photons. What will remain is a universe unimaginably vast, cold, and dark, populated only by a dilute sea of fundamental particles and photons, all at nearly the same, infinitesimally low temperature. There will be no places hotter or colder, no structures, no change, no flow of energy to do work or power thought. It will be a state of perfect, uniform equilibrium, a silent, eternal stillness. Before such a vision overwhelms, let us conclude with a fifth, grounding fact. This future is not our present. It is a projection based on the physics we understand today, extrapolated over timescales so immense they hold no practical threat, only a philosophical weight. In the same way that the death of a star billions of years from now does not diminish the warmth of our sun today, the heat death of the universe does not diminish the vibrant, structured, and awe-inspiring reality we inhabit now. In fact, it throws our present moment into brilliant relief. We exist in the cosmic springtime. We live in the narrow window of time after the first stars have lit up and before the last ones have died. In the epoch where matter is organized into complex forms, where light fills the darkness, and where consciousness can arise to witness it. The very fact that we can contemplate this distant, cold fate is a testament to the vibrant, energetic, and structured phase of the universe we are privileged to be part of. So, as we consider this slow drift toward equilibrium, let it not be a source of melancholy, but of deep, quiet appreciation for the fleeting, beautiful, and dynamic cosmic moment in which we find ourselves alive and aware. After contemplating the universe's distant, cold future, a natural and deeply human impulse arises to turn our gaze not outward to the end, nor backward to the beginning, but inward to the significance of our own fleeting presence within this grand narrative. We have journeyed to the edge of light and time, traced the architecture of dark matter, and witnessed the slow fade of all things. Now we come to a resting point, a moment of synthesis, where the cosmos ceases to be an external spectacle and becomes a story of which we are an intimate part. Let us begin this homecoming with a fact that is both scientific and deeply poetic. Every atom in your body, other than the primordial hydrogen, was forged in the heart of a star. The carbon in your cells, the oxygen in your breath, the iron in your blood, the calcium in your bones, all were created through nuclear fusion in stellar cores or in the cataclysmic explosions of supernovae. These elements were then scattered across space by stellar winds and explosions, eventually finding their way into a nebula that collapsed to form our sun and its planets, and ultimately into you. You are not just living in the universe, you are literal stardust, the universe temporarily arranged into a form that can think and feel and wonder about itself. When you look up at the night sky, you are not a stranger looking at distant fires. You are a piece of those fires, looking back at home. This leads us to our second, more philosophical fact. In a universe vast beyond comprehension, we represent a rare and remarkable phenomenon, a part of the cosmos that has become self-aware. The astronomer Carl Sagan famously said, "We are a way for the cosmos to know itself." This is not mere poetry. Through our senses, our instruments, and our minds, the universe has developed a capacity to observe its own laws, to trace its own history, to marvel at its own beauty and terror. The photons that have traveled for billions of years from the edge of the observable universe end their journey not just on a telescope sensor, but in a conscious mind that can interpret their story. In this quiet, profound sense, the universe is not empty and meaningless. It is experiencing itself, questioning itself, through us. Our curiosity is the universe's curiosity. Our quest for the edge is the universe exploring its own boundaries. But where is the center of this grand exploration? Our third fact offers a humbling and liberating correction. There is no center. We have moved beyond the ancient egocentric model of the cosmos. The universe has no central point, no privileged location. The Big Bang did not happen at a single point in space. It happened everywhere. It was the rapid expansion of all space from a state of extreme density. Every point in the universe can rightfully say, "The Big Bang happened right here," and every observer on any galaxy sits at the center of their own observable sphere, bounded by their own shell of CMB radiation. This means your location right now is as central as any place can be in the cosmos. You are not on the outskirts of a great empire. You are, in the only meaningful way, at the heart of your own perceptible universe. This democratization of perspective dissolves any feeling of cosmic insignificance. You are not peripheral. You are a focal point of observation. Our journey through time also requires a similar correction, which is our fourth fact. Time itself had a beginning. We are used to thinking of time as an infinite river flowing from the past to the future. But according to our best physics, time, as we understand it, began with the Big Bang. Asking what came before the Big Bang may be as meaningless as asking what is north of the North Pole. The concepts of before and after require time to exist. The singularity at the Big Bang represents the boundary of space-time. This means that all of cosmic history, every event, every star's life, every planet's formation, every moment of human history, exists within a finite duration of time, a story with a first page. Your life, your thoughts, this very moment, are woven into that finite yet immense temporal tapestry. You are not living in a small slice of eternity. You are living in the unfolding of a story that has a definitive starting point, a story in which you are a character. We culminate this reflective section with a fifth, synthesizing fact that brings the cosmic and the personal into a gentle unity. The boundary between the universe out there and the universe in here is an illusion. The same physical laws that govern the orbit of galaxies govern the electricity in your neurons. The same quantum fluctuations that seeded the first structures in the cosmos underpin the chemistry of your brain. The silence of deep space and the quiet of your room are not opposites. They are connected by the same physical reality. When you close your eyes and drift towards sleep, the vast, dark, silent cosmos does not go away. It is present in the very atoms of your being, in the rhythm of your breath, in the electrical storms of your dreams. The exploration of the edge of the observable universe is not a voyage away from yourself. It is a voyage into the deepest nature of what you are made of and what surrounds you. The immense distances and timescales are not a measure of our smallness, but a measure of the profound, intricate, and beautiful process that led to this moment of conscious rest. As you settle deeper, feel not small but connected, a temporary thinking pattern in the ancient, ongoing story of stardust, a quiet witness at the heart of your own observable world, breathing in time that had a beginning and resting within the same laws that spin the galaxies. As we near the conclusion of our quiet voyage, the hard edges of facts and figures begin to soften, like distant mountains blurring into the evening haze. We have gathered 100 glimpses of the cosmic frontier, but now, in these final moments of wakeful exploration, let us allow those glimpses to settle into something more like feelings, more like reflections. Let us trade measurement for meaning, not by abandoning science, but by seeing it as the pathway to a deeper, quieter awe. Our first reflection is on the very idea of the edge. Fact 65. The universe has no edge in the way a map has a border. What we call the edge is simply the limit of our perception, a horizon built from time and the finite speed of light. There is no wall, no sudden drop into nothingness. There is only more universe, forever receding from our view, its details lost to the expanding dark. This means we are not trapped inside a finite bubble. We are simply sighted beings in an ocean too vast to ever fully illuminate. The frontier is not a barrier, but a testament to the grandeur that lies beyond our grasp. It is a gentle reminder that mystery is not a failure of knowledge, but its constant companion. Embrace that mystery as you would the soft darkness behind your eyelids. It is not empty, but full of potential. Now, bring your awareness to the light itself, the messenger that has made this entire journey possible. Fact 66. The photon that lands on your retina from a distant star has been traveling for years, centuries, millennia. But some of the faintest glimmers in the void have been on their journey for over 13 billion years. Consider that. The light arriving at our telescopes now from the most distant galaxies began its voyage when the universe was in its fiery infancy. It has traversed an ever-widening gulf, past the gravitational wells of emerging galaxies, through the silent tides of dark matter, all while the very space through which it moved was stretching. That it arrives at all is a miracle of persistence. And in this moment, as you listen, ancient light from the edge of time is falling onto our planet, invisible to your eyes but real. You are being touched by the universe's deepest past. It is a connection as intimate as it is immense, a whisper from the dawn, reaching across the ages to find you here, now in the quiet. This leads us naturally to fact 67. Every clear, dark night sky is a living museum, a free exhibit of cosmic history. When you look up, you are not seeing a single moment, but a layered tapestry of time. The bright star is a recent letter. The fuzzy patch of a galaxy is an old postcard. The darkness between them holds the untold stories of epochs before the first star was born. There is no present view of the cosmos. The sky is a palimpsest, with the newest light written over the oldest, all arriving together in a silent, glorious cacophony. To stargaze is to time travel. You need no machine. You only need to look up and let your mind drift along the beams of light, each a lane into a different chapter of the universal story. Your backyard, your rooftop, your window, all are portals to the past, making you an archaeologist of light every time you glance upward. And what of the mind that does this gazing? This brings us to our final, more speculative reflection, fact 68. In a universe that has evolved from simplicity to staggering complexity, your dreaming mind is its own kind of cosmos. Within the neural networks of your brain, electrical storms ignite constellations of thought. Memories coalesce like nebulae, and narratives unfold in the private space-time of your consciousness. While not bound by the physical laws of the external universe, this internal cosmos is made from its stuff, powered by its energies. In sleep, as you drift from the waking world, you embark on an inward voyage that mirrors our outward one, into uncharted territories, past the edges of logic, through landscapes of emotion and symbol. Your dreams are a personal, experiential echo of the universe's own capacity for creation and exploration. They are a reminder that the curiosity which drives us to map the edge of the observable universe is the same force that crafts the strange, beautiful worlds behind our closed eyes. Let these four reflections merge now into a single, quiet understanding. The journey to the cosmic edge and the journey into the self are not opposites. They are complementary explorations of reality. One uses telescopes and mathematics. The other uses introspection and wonder. Both are valid. Both are human. Both seek to understand the nature of existence, of boundaries, of light, and of story. As we prepare to let go of the narrative thread, to release the facts and figures and allow the mind to float freely, carry with you this dual sense of scale. You are both infinitesimally small in the vastness of space and time, and you are the entire universe experiencing itself in a singular, irreplaceable way. There is no contradiction here, only a beautiful, humbling, and ultimately peaceful paradox. The final section awaits, not with more information, but with a gentle release, a slow return from the depths of space to the quiet harbor of your own restful awareness. We have traveled from the familiar glow of our night sky to the very limits of light and time, and back again. We have sailed past galaxies, through voids, and up to the shimmering curtain of the cosmic microwave background. We have peered into the opaque darkness that preceded it, grappled with the invisible dominance of dark matter and dark energy, and traced our place within the grand, flowing web of Laniakea. We have met the tools of our discovery and confronted the great unanswered questions that linger at the frontier. We have looked ahead to the universe's cold, distant future and reflected on our own warm, stardust nature within its story. Now, as all journeys must, this one finds its gentle end, not with a grand conclusion, for the cosmos offers none, but with a slowing, a softening, a final gathering of the remaining sleepy facts we have collected along the way. Let them be not detailed explanations, but gentle echoes, images to hold in the mind as it drifts. Here are the remaining facts, numbers 69 through 100, brief glimpses of the wonder we've explored. 69, the observable universe is a sphere, but the full universe may be infinite. 70, cosmic inflation, a burst of faster-than-light expansion, likely shaped our early cosmos. 71, eternal inflation suggests the possibility of a multiverse. 72, extraspatial dimensions may be curled up at scales too small to see. 73, the horizon problem, why the universe is so uniform, is solved by inflation. 74, the flatness problem, why space isn't curved, is also solved by inflation. 75, the cosmic microwave background radiation passes through you right now. 76, the Planck satellite mapped the CMB's tiny fluctuations in exquisite detail. 77, the universe is 13.8 billion years old, a number derived from the CMB. 78, the cosmic recipe is 68% dark energy, 27% dark matter, 5% ordinary matter. 79, hypervelocity stars are exiled from their galaxies by black hole encounters. 80, orphan galaxies live in lonely isolation within vast cosmic voids. 81, supermassive black holes reside at the heart of nearly every large galaxy. 82, gamma-ray bursts are the universe's most powerful explosions. 83, a light year is a measure of distance, not time. 84, look-back time means we see objects not as they are, but as they were. 85, cosmological redshift is the stretching of light waves by expanding space. 86, a cosmic event horizon defines galaxies whose future light will never reach us. 87, gravitational lensing bends light around massive objects. 88, Einstein rings are perfect circles of light caused by strong gravitational lensing. 89, dark matter is detected only by its gravitational influence. 90, dark energy is causing the expansion of the universe to accelerate. 91, the Milky Way contains 100 to 400 billion stars. 92, our solar system orbits the galactic center every 230 million years. 93, Earth moves around the Sun at 107,000 kilometers per hour. 94, the Sun bobs up and down through the galactic plane. 95, the local group contains about 54 galaxies. 96, the Virgo supercluster is our larger galactic neighborhood. 97, the Laniakea supercluster is our immense heaven, spanning 520 million light-years. 98, we are drifting toward the Great Attractor. 99, the cosmic web is a sponge-like structure of filaments and voids. 100, our place in the cosmos is profoundly, comfortingly typical. And with that, 100 glimpses of the edge are complete. The story is told. The facts are laid gently to rest. Now, let everything we have spoken of soften. Let your awareness, which has journeyed so far, now begin its return. Release the vastness of interstellar space. Let go of the swirling galaxies, the silent dark matter threads, the ancient, cold light of the cosmic dawn. Feel your mind's eye turning away from the infinite and the eternal, drawing slowly back to the confines of this room, to the feeling of your body resting against the bed, to the rhythm of your own breath. With each slow exhalation, let a layer of the cosmos drift away. Exhale and let the distant quasars fade. Exhale and let the great walls of galaxies dissolve. Exhale and let the whispering photons from the edge of time complete their long journey and be at peace. There is no more to see, no more to know in this moment. The universe is vast, and it will be there tomorrow, and for billions of tomorrows after that. Now, bring your attention to the simple physical reality of here. The weight of the blankets, the slight coolness of the air on your face, the distant, muffled sounds of the world at rest. Your breath, in and out, a quiet tide in the harbor of your body. With every breath in, imagine drawing in a sense of quiet wonder. With every breath out, imagine releasing any last vestige of thought, of analysis, of seeking. Just breathe, just be. A conscious collection of ancient stardust, resting in the deep, quiet night. Let the words you have heard become like distant chimes, their meaning fading, leaving only a resonant, soothing tone in their wake. Let your thoughts be soft, slow clouds passing through a calm, dark sky. There is nowhere to go, nothing to solve. The exploration is over. All that remains is this perfect, peaceful stillness. Allow your eyes to be heavy, your limbs to be loose, your mind to be a still, dark pool reflecting nothing but the gentle, starless peace of deep sleep. Approaching now, wave upon slow, silent wave, just resting, drifting away.